Hello and welcome to section 3.4 on rates of change. In this video, we explore examples to see how the derivative, the instantaneous rate of change, can be applied to a variety of fields. The following examples are presented so that you will acquire the ability to recognize rates of change and thus derivatives arising in the sciences. What is the current of a stream? How do we characterize this in a way we can quantify? The speed with which water moves along a stream is related to flow. Suppose a bridge crosses a stream. The function w will represent the total amount of water in the stream which passes below the bridge on the time interval 0 to t. The current of the stream is the rate at which the flow changes with respect to time t. That is, the change in volume with respect to the change in time. We can discuss the average current just as we do the average rate of change. And we can discuss the instantaneous current as the limit of the average current. To summarize, the derivative of the flow is current, just as the derivative of position is velocity. Similarly, given a charged wire with an excess of electrons on the left and a deficit of electrons on the right, we can measure the amount of charge that has passed a sensor from time 0 to time t. Q of t is the flow of charge, just as W of t was the flow of water. As with flow, the current along the charged wire is the rate of change in the charge Q with respect to time t. And as before, we have the average current for the average rate of change and the instantaneous current for the limit of the average currents. Let's return to the example with the flowing water. As you've probably noticed in real life, the current of a stream is not uniform. There are many factors determining the current of a point, but typically, the current is the fastest near the middle of the stream and slowest near the edges of the stream. Friction and turbulence slow the water down near the shore and the stream bed. Let's simplify our setting from a stream to liquid flowing through a smooth cylindrical tube. The liquid will flow from high to low pressure, and the axis of the tube is the line passing through the center of the cylinder. Liquid near the walls of the tube will move slower than liquid near the axis. This is described by the law of laminar flow. Let P represent the pressure difference between the left and right end of the tube. Let eta represent the viscosity of the liquid. Let L represent the length of the tube, and let R represent the radius of the tube. The law of laminar flow is the velocity of a liquid at a certain distance, little r, from the axis. Question: how fast does the velocity of the liquid decrease as we move from the axis to the wall? That is, what is the trend in velocity from v1 to v2 to v3 to v4? What we are looking for is the change in velocity v with respect to change of radius from the axis little r. dv over dr is called the velocity gradient. We can calculate the velocity gradient by taking the derivative with respect to little r. Notice that the equation only possesses two variables, the velocity v, which depends on the radius from the axis little r. We will assume that the tube is fixed, thus L and big R are constants. The liquid has been chosen, hence eta is a constant, and the pressure on each end is constant, hence P is constant. Therefore, we can take the derivative with respect to little r. Notice that the left part of our expression is constant, hence as a derivative that will be 0. Recall that our variable is little r, the distance a point is from the axis, and the velocity gradient is what measures the change in v as we move a point away from the axis. Also notice that the radius big R plays no part in the velocity gradient. As the point moves farther away from the axis, little r increases and the velocity gradient becomes more negative. That is, as you get closer to the wall, the speed of the liquid decreases. It has a negative derivative. The slowdown is twice as fast in a tube with twice the pressure, as you can find pressure, P, in the numerator. The slowdown is half as fast in a tube, which is twice as long, as L is in the denominator. And the slowdown is half as fast in a liquid which is twice as viscous, as eta is in the denominator. The equation allows us to see how two different parameters affect the velocity gradient. Rates of change are not restricted to the natural sciences. For example, In economics, the concept marginal cost is a rate of change. Suppose a company produces widgets. What will happen to production costs as the number of widgets produced changes? We will let C of x be the cost of producing x widgets. Typically, the function C is the fixed costs plus the variable costs in producing a single widget, plus the variable costs in producing a widget. Fixed costs are independent of the number of widgets produced, such as administrative salaries, storage, and factory rentals, while variable costs are dependent upon the value x, the number of widgets produced. The marginal cost is the rate of change associated with the cost function C. We can find an average marginal cost, but does it make sense to discuss instantaneous marginal costs? Delta x is the change in the number of units sold, so you would always expect it to be a whole number. In fact, the function C should only make sense on whole numbers. How would you make a negative number of widgets, or 1/10 of a widget? Even though C has domain errors, in practice, the cost function is a polynomial, hence the derivative will exist. In summary, whenever we find an equation of variables, we can find rates of change for those variables. In the natural sciences, we have velocity as the derivative of position, and current as the derivative of flow and charge. Also, in the social sciences, like economics, we have marginal cost representing the derivative of cost. The takeaway for this video is the importance for rates of change and derivatives beyond abstract mathematics. You've seen the basics, now work towards mastery through practice and study.